Okay, so these are the three equations we use when it comes to linear motion, motion in one dimension. So when a question is given to you, you look at the information given from the question, and then you pick the one that is suitable to help us solve the problem. Please, are you fine?
Yes, please.
Good. So looking at what I have the initial velocity, I have the final velocity, I have the time, and I'm calculating the distance or displacement s. Girls, looking at the three equations, which one do you think will be suitable to solve our problem?
Equation 2.
Equation 2. Let's see why equation 1 will help us. The question, if we use equation 1, the question is about distance. This equation doesn't relate to distance. We are finding out acceleration and time. So because what demands of isn't part of
Mr. Da, please, your voice is.
come again.
Please, I said your voice is breaking.
Oh, is it better now?
Yes, please.
Okay, so I'm looking for distance. This equation has nothing distance within. And so straight away, this one is out. All right. All right.
Yes, please.
I think there's a question. Yes. Go ahead. What's the question? Or maybe it's a mistake. Okay. Let's look at equation 2. If we can use equation 2, but until we've calculated for the acceleration A, we cannot use equation 2. But the good thing is that we can use equation to find acceleration. So we can use equation 2. Are we fine? So A equation 1 B acceleration equal to 25 meters per second.
Mr. Da, please, your voice is breaking.
My voice is breaking. Oh,
Yes, please.
oh, what's the problem? But it's better. Hello? Hello?
Yes, it's okay.
Yes.
Okay. So 25 minus 0 divided by time of 20 seconds. What is 25 divided by 20? That will be 1.8. 1 point what? Hello, are you there?
Yes, please.
1.25
25.
meter per second square. So we have the acceleration, meaning we can use equation 2, sorry, 3 to find x, the distance. Now help me make s the distance from equation 3. From this equation, help me make s the distance, the subject.
V squared minus
V squared
minus
minus
U squared
U squared
divided by 2A.
2a. Good. So let's now substitute our values. We have the final velocity 25, the initial velocity is 0, so 25 squared divided by 2 times the acceleration, which is 1.25. Okay, multiply, divide, and give me the final answer for displacement or the distance covered by the body. So 25 squared divided by 2 times 1.25. What's your final answer? What's your final answer? Let's be quick. So 250 meters. But we can actually, based on what we have, we can use equation 2 direct. And what is equation 2? Ut plus kt. Okay. So because we have u is 0, so exponent or this term of the equation goes to 0. So once this is 0, it means
Mr. Dia, please, so the voice is
this voice. I think it happens when I tend to face the board.
Hey, Mr. Dia, as for me, I can't see you at all. It's black.
Please, is that a general problem?
No, please.
no, please.
Then please rejoin. If you can't see me, then I think it will be a network problem at your end. Quickly rejoin for me. Mamiefwa, your hand is up. How do I help?
Please, I don't understand from the after solving the solution, the speed also. I don't understand the v square minus.
Don't worry, we are coming to go through the nitty-gritties of equations of motion, so you understand better. We are just applying because somebody asked the question, right?
Okay, thank you.
All right. So, we have found acceleration. Acceleration A is 1.25. So the square of the time. And the time is 20 seconds. So 20 plus 1.25 times 400 divided by 2. 20 squared is 400. So this goes in 1.25 times 200. And what is 1.25 times 200? Because 1.25
250.
yes. 2.5 times 100. Whichever way we look at it, the value is what? The value is what? The same. All right. Okay.
Yes,
Okay. So let's go into what we have for today. Let's look at what we have for today. Do I clean the board?
no, please.
Please, if you are writing it, quickly do so, and then let's move on. Hello? Hello?
Hi.
My voice is not breaking, right?
Yes, please.
You have to maintain it. It shouldn't break. Do I clean the board?
Mr. Dia,
Hello?
please, so how are you supposed to know that these 3 formulas are the ones which you choose one from to solve the question?
Don't worry. We are now coming to swim into the ocean properly. Okay.
Yes, please.
So you get to understand the varying depth within the ocean so as to decide where to swim and where not to swim. Alright. I'm training the board though. Mhm. Yeah, but are you there? Hey, some of you haven't been submitting your assignment. Some of you keep your assignment. It's not a good thing. Eh? Your parents will hear. Oh. If you don't want me to tell them, please be submitting your assignment and on time, right? Okay, so last time we were looking at equations of motion. So we saw a displacement time graph, a uniform velocity motion, a non-uniform velocity motion, and then a stationary motion. We also got a chance to understand velocity time graph, okay, velocity time graph. And the velocity time graph, we looked at uniform accelerated motion, non-uniform accelerated motion, okay, and then and all that. When the body has a zero acceleration, we got to understand and all that. Today, I want to quickly apply one of those things we are looking at. Take your view. The motion is this. We have this motion. This is a displacement time graph. So a graph.
Yeah, please.
Pardon?
Mr.
Hello?
Edward, please.
Hey, this your voice is breaking, then it will be fine. I think it happens when I have to turn to the board. Okay. So let's manage with it. It happens when I have to turn to the board, and I'm wondering why that I have that challenge today. So I want us to quickly go through these two kinds of graphs of motion. Yes. So this is the first motion of a body. I want to help us go through this motion. What is the whole motion about? Volunteer help us understand graph of motion. Yes. Who would volunteer for us? What kind of motion is the first one? Quick one. Let's not waste time. About 5 minutes.
Distance time graph.
Please mute yourself. Okay, mute yourself. Go ahead. Whoever was on the floor should continue. Yes, is that this one is?
Distance time graph.
Yes, it's a distance or displacement time graph. But explain, describe motion for us. Describe the motion for us. Maybe she's still engaging the brain. Somebody else should try. A try by somebody else. Yes. Ajua Sante, Ajua Sawa, Adelaide, Abba. Give it a hand. Describe this motion for us. Abba. against Bedu Bushel. Okay, Gloria, you are ready.
Okay, please, a body started moving with a constant velocity. Then it got to a point where it stopped moving. Then it started decelerating.
Okay, Gloria, nice try. Okay, Addison, Lizzie, go ahead.
Okay, a body starts from rest and then uniformly accelerated.
Which one? Is it A or B?
A.
Okay.
A body starts from rest and uniformly accelerated to a certain point and then
Abba.
moved in a,
Uh-huh.
and moved from and then moved with a constant velocity to a certain point and then decelerated.
Okay. You see?
Uniformly decelerated.
Okay. Please, class, if we have, whenever we have a distance or displacement time graph, we shouldn't be talking about acceleration until it's a non-uniform situation. If it's a non-uniform situation, then we can be talking about acceleration, but not when it is uniform. Please, I hope you get what I'm trying to say.
Yes.
Yes.
Okay. Okay. You see, because the slope of a displacement time graph is equal to the what? It's equal to the velocity or the speed. Whenever we are talking about displacement or distance time graph, we shouldn't be talking about acceleration. The only point where we can talk about acceleration is when we have a non-uniform velocity motion. Because the velocity at every instant, aka instantaneous velocity, increases, we can be talking about an acceleration or a deceleration. That's the only situation where we can talk about acceleration under a displacement time graph, but not when the motion is uniform. I hope we are okay.
Yes.
No, please.
All right, so let me take this up. You see, what will you say about this side? The side A, B, C, D, and E. What will you say about the interval from A to E? Yes.
There is a uniform velocity.
So there is a uniform velocity, meaning that the body does what?
Moves.
Yeah, but describe it further. Meaning that the body
moves with constant velocity.
Oh yes, constant velocity, because this angle is constant, theta is constant. But it means that within the interval from A to B, the body covers equal distances within equal time interval. And that is why we have a constant or uniform velocity, okay, from A to B. Please, are we okay?
Yes, please. Yes, please.
So in describing this, this is how I will go. From a point A to B, the body covers equal distances within equal time to interval, and so has a uniform velocity from A to B. That is how I'll describe it. Then from B to C, Xavier, what happened? From B to C.
The body is at rest.
The body is at rest. Why? Why? Because the distance covered at the third interval is the same from B to C. Then from C to D, what happens? Yes, a volunteer to come in. Okay, from B to C, C to D, what happens?
The displacement of the body decreases within equal time interval.
Exactly. The body's displacement decreases within equal intervals within time. So we have the body's displacement reducing within equal intervals within equal time as well. And what will you say about the velocity of the body there? What will you say about the velocity of the body?
It is negative.
Yes. So there is a uniform velocity there, but in the opposite direction. That is why it's a what? That's why it's a what?
A negative.
That's why we describe the velocity there as a negative. All right. From D to E. So here, the velocity, okay, what happens? What happens to D? Okay, from D to E.
The body's displacement increases with equal time in the different direction.
Exactly. The body's displacement increases. You see, from C to D, there is a drop in the displacement of the body. So at this point, at point D, what is the displacement of the body? At point D, what's the displacement? Zero. Good. At point D, the displacement is 0. Then from D to E, the body's displacement increases within equal intervals with time, but in the opposite direction. So that's it. Any question? No question. Let's move on to the second graph. But you see, whenever you are given a graph to describe, please, the first thing you have to look out for, what kind of graph is this? Is it a displacement time graph or velocity time graph? It being any of this would inform your description, what you have to say. Ewesi, your hand is up.
Mr. Edia,
Hello.
please, can you repeat what you said about the distance from D to E?
From D to E, at the point D, the body's displacement is 0.
Yes, please.
Okay. The body's displacement is 0. But from D to E, the displacement is increasing within equal time interval. So over here, the body is still moving with a uniform velocity, but in the opposite direction. Okay.
Yes, sir.
Good.
Thank you very much.
Welcome. B, motion B. Somebody to break the ice for us. Okay. Safua, start for us.
With a B, the body started with a uniform acceleration. That is the velocity.
Safua, I'll just hold your throat there. You are missing something so important. You are missing something that is so important. Safua, are you there?
I said the body started moving with a uniform velocity with.
No, I won't buy it. What has she missed? What has she missed here? Class.
A body from a start from a rest.
Come again.
A body started from rest.
A body starts from rest. Very, very important. Telling you that the body's initial velocity is 0. And that is it. Whenever the graph of motion starts from the origin, then it means the body starts from rest. If it starts from rest, it means the initial velocity is 0. Safu, are you okay?
Yes, please.
Okay, then I can allow you to continue. So start and then
Okay.
continue.
A body starts from rest and has a uniform acceleration. That is, the change in velocity with time was constant.
Okay.
Then that is from A to B, it was constant. Then when it got to B to Mr. Da, please, you're labeling the other B, won't it be C? B to C.
Yes.
Okay, so from B to C, it also rested at that point. Then from C to D, it did.
Sapua, is that from B to C? What happened?
It stopped moving.
What starts moving?
Like it was. No, the body stopped at that moment.
I won't buy. I won't buy that. I have somebody to quickly correct that. Yes, if you've made an observation, go ahead. From B to C, what is happening?
From B to C, the body was moving with a constant velocity but with 0 acceleration.
Exactly. So somewhere from B to C, the body is moving with a constant velocity. So it maintains the speed from B to C. Safu, are you there?
Yes, please.
Are you okay?
Yes, please.
Okay, so start from A.
A body started at rest, and a body at rest started moving with a uniform acceleration. That is, a change in velocity with time was constant. And when it went from B to C, the velocity was constant without any acceleration.
With 0 acceleration.
Then with zero acceleration. Then from C to D, it started decelerating with constant velocity with equal time.
So from C to D, the body decelerates uniformly. A to B,
The body decelerated uniformly.
From A to B, the body accelerates uniformly. C to D, the body decelerates uniformly.